today we'll discuss about automorphism. Sorry, inner automorphism. In previous video you have seen about automorphism and some properties like that. So today we will discuss automorphism. Okay, so today we'll discuss about automorphism. Let's forget about automorphism. Let me define a map. Let G be a group. Okay, let me define a map first. FA is from G to G. Okay, whenever I am writing G, it by default it should be understood that I am G by means I am considering G as a group. Okay, so that means I am expecting from you, because you are starting on automorphism, inner automorphism, you must be able to aware what is G, what is a function. So G is a group. I am considering G, always I will consider G as a group. Okay, capital G as a group, and FA is a function from G to G. I am defining FA in such a way that FA at any element x actually gives us AX A inverse. Can you see this map is an well-defined map? Check, this map is an well-defined map, and I am defining another set, not a group, not an group. I am defining another set which is denoted by in of G. This is actually called inner automorphism of G. All those FA in such FA, okay, such FS. So FA of x, FA at any point x inside the group G is actually gives us AX A inverse, and for all A inside the group G. Okay, this is called an inner automorphism. Okay, can you verify this is going to be a group? Verify yourself. The verification is very easy. Verify yourself that in of G is actually a group. In fact, this is a subgroup of automorphism of any group G. Okay, anyways, you just show this is a group. Okay, so today I will show the inner automorphism of any group G is isomorphic to G by ZG. We'll show inner automorphism of any group of any group G is actually isomorphic to G mod ZG. ZG means, what do you mean by ZG? ZG we already know. ZG is a center of a group. Okay, all those elements inside the group G which commutes with every element of G. Okay, so this is called the center of a group G. Okay, so now inner automorphism of G, we need to show this. We'll show this. Okay, so define another map. Define a map. This is called capital Phi, is from G to inner automorphism of G. How the actual inner automorphism of G group look like? They actually look like this. Okay, So how will I define the map Phi? Phi of any element. Okay, Phi of any element A inside the group G is actually gives us FA. Okay, this map is a well-defined map, and verify Phi is a homomorphism. What do you need to check? Just you need to check that Phi of any two element you take A, B, this actually gives us Phi A and Phi B. You will just show what we have. Phi of actually AB is actually FAB. You just show it FA compose FB. You just show it, then you will be done. This is actually it will be actually nothing but Phi of A, Phi of B. Okay, Phi of A compose Phi of B. Sorry, composition. Of course, this is composition. Phi of A is a map FA. Of course, these are so composition. Okay, you just show this. Then you will be done about the homomorphismability of a group. So let's check. I will show this two part. F of AB. What do we mean by F of AB? F of AB is actually gives F of AB at any point x. You will be just giving AB x AB inverse. Okay, sorry, AB inverse, whole inverse. Okay. Now what about FA? Compose FB at any point x. That means FA of FB of x means B x B inverse at any point, and this is actually nothing but what is this? That means A B x inverse B x B inverse and A inverse. This is actually nothing but AB x and AB their inverse. Don't you think? Because AB their whole inverse is actually nothing but B inverse A inverse. You are already know. Okay, you are already aware. So this is actually nothing but F of AB. F of AB is actually nothing but phi of AB, and these are actually nothing but phi of A compose phi of B. Okay, so what we have eventually get, that phi of AB is actually phi of A compose phi of B. So phi is a homomorphism done. Homomorphism, it is a homomorphism. Okay, now we are letting out with, is it a onto or 1-1? So you see the map first. Check for the onto-ness first. Onto-ness, I don't think that onto-ness I have to show, because this is a very trivial onto. Trivially it is clearly visible that this map is going to be onto. It means that onto means if you give me any element over here, I should be able to give you any a pre-image inside the group G. If I take, okay, let's try, let's prove formally what is onto. What do we mean by onto-ness? Let F or GB, sorry, if you take GA be any arbitrary element of inner automorphism of G, right? You should be able to give me an element under the map phi. Okay, this should give us GA. What I can take? You can take A. Yeah, that's it, nothing else. Okay, if you take GB inside the element B, if you take GB over here, then you take just B to be here, B to be inside the group G. This means that this map, this phi is onto. What about 1-1-ness? 1-1-ness, is it a 1-1? Is it 1-1 or for isomorphism we don't need 1-1-ness? No, sorry, we need 1-1. So okay, is it 1-1? We just wanted to, for isomorphism, if you remember, I have in previous lecture I have proved about first isomorphism theorem. That means G by kernel phi is a map. Kernel phi is actually isomorphic to image of phi, is not it? Okay, so if this is onto na, if phi is onto this will definitely imply that the image of phi is actually inner automorphism of G, because this is the actually codomain, and codomain will be equal to range, because the function is going to be onto. The function is onto, right? Because the function is onto, this means image of phi is actually inner automorphism of G. We just we don't need anything but 1-1-ness. We don't bother about that, whether it is going to be 1-1 or not. We don't bother about that. We just need to we just will see that its kernel, because we are trying to apply the first isomorphism theorem over here, right? Okay, this is we are going to. So let's take the kernel of phi. What do you mean by kernel? Kernel means all the elements inside. Kernel means all the elements, because the map is from here. All the elements inside the group G, such that the f phi of this any element this is going to the identity of this inner automorphism, right? So we can write all those elements A inside the group G, such that phi of A actually gives identity of inner automorphism. Identity of inner automorphism, okay? Which what we don't bother what is this. Actually identity map is actually nothing but the element actually gives us the element X, nothing else. Okay, so what is this A inside the group G, such that phi of A? What do you mean phi of A? Phi of A money means that FA. What is FA? FA is A X A inverse. This actually gives you X, because identity is always X. In any element X, it should go to in X. Okay, at any element X, it should go to X. So so this which is what is this A? All those elements at G, such that AX operate A inverse A in the right from right hand side. Here it will be A, and here it will be A inverse A gives you identity. That means AX equals to XA. Okay, so all those elements inside the G group has that which commutes with every element inside the group G, or which commutes with X. So don't you think this is the center of a group? This is the definition of center, na? This is the definition of center, right? So kernel of phi, which is actually center of the group. So now we can apply the first isomorphism theorem. Apply first isomorphism theorem by applying first isomorphism theorem. What is G? We have G. What it says actually, G mod kernel phi is actually isomorphic to image of phi. This is actually first isomorphism theorem. What is our G? So this implies that G is G, and kernel phi, what is our kernel phi, is actually ZG, is isomorphic to what is our image, because image of phi is actually where we have calculated image of phi. This is image of phi. Image of phi is actually inner automorphism of G. Enough G. Okay, so the proof is done, right? So for any group G, and G by ZG is isomorphic to inner automorphism of G. If you inner automorphism of G, if you have any group G, and if the question says that find the inner automorphism of G, you can directly predict by this function, this relation G. You need just G, and you just need the group ZG. You will definitely able to see the inner automorphism and the internal properties of this. Okay, so I am giving a little example over here. Okay, example. So example, you can take, if I take the group Q8, G is Q8, right? Q8, sorry, not Q8, yeah, Q8. Find, oh sorry, not automorphism, inner automorphism of Q8. So as simple as that, just apply this. What is g? G is q8. And what is zg? Z of q8, do you know, is actually plus minus 1 na? Plus 1 minus 1, that it contains actually two elements. Okay, so two elements. So gy zg, order of gy zg. Gy zg means q8 by z of q8. Sorry, you can take to be order of q8 by z of q8. q8 is actually, what is happening? q8 is actually 4, right? Because q8 is of order 8 and z of q8 contains two elements, so 8 by 2 is actually 4. This is actually nothing but 4 order. We have only one element, only one group of 4 order, which is actually k4, right? We have only one group of order 4, which is k4. This is going to be abelian. Okay, so now if I this, so inner automorphism of G, inner automorphism of G of q8 is actually isomorphic to k4, because g by zg means q is q8 by z of q8. This actually contains 4 elements, so 4 elements we have only one group. This is k4. This is called Klein's 4 group. So this is actually isomorphic to k4. Okay, you can yeah, this is one example. You can create many examples, so you don't need to worry about that. You just if someone says any inner automorphism any group G, you don't need to bother about that. You just find the center of this group and apply this theorem, G by zg, and you will definitely make some conclusion from this. Definitely, I can definitely say. Otherwise, inner automorphism G, its handling is little bit difficult. So okay, so that's what is for today. We'll meet later, and thanks for watching. Okay.